Gentlemen, welcome to another fun episode of Equations of a Circle. If this looks familiar, it should. Now let's try to tie all the formulas together that you've seen so far, and some of the Euclidean, and possibly it'll look like trig, so really kind of a really overlap section here. For today's work again, what you'll need to have with you is a pen and pencil, notepad, a calculator. I've given you parts of the formula sheet that you'll need, and yeah, let's get going. First things first. Let's have a look at how do we find the equation of a circle when its center is at the origin. Now in this drawing on the left, you've seen something like this before. It looks very similar to what we would have done when we drew the unit circle for trigonometry. It also has a right angled triangle, and I suppose that means really if we did one piece of information that you know from right angled triangles is that x squared plus y squared equals r squared. And the reason why that would be true, we would say Pythagoras. And wonderfully, this is actually the equation of a circle, because it would make no difference wherever you place that right angled triangle in any of the quadrants. It would always be true that x squared plus y squared would equal r squared. And so what it comes down to for any circle, the most important pieces, let's just make a note here, the most important pieces of any circle. First important piece is where is it centered, and the second part is what is its radius. So really, where is it and how big is it? In this drawing, the circle center is at the origin, 0, 0, and its radius is r. So the equation of a circle at the center is x squared plus y squared equals r squared. Really straightforward. Let's have a look at some questions on this. First questions we're going to look at today. A circle with a center OO, so at the origin, passes through 2 points, minus 5 and 5, and 5 and minus 5. Plot these points and draw a rough sketch on the circle, determine the equation of the circle, calculate the length, and then explain why the length is the diameter. Let's do this in pieces. First part, I'd like you to pause the video right now and sketch this diagram. Draw a circle that's centered at 0, 0, and passes through these 2 points. Go for it. Okay, good. So you should have something like this, points P and Q. And what we notice about these points P and Q is that this is minus 5 and 5, and this is the points 5 and minus 5. And you really now need to start to look at these things, because these 2 points are the mirror images of each other. The x and y values have been mirrored on the y equals x axis. So this is our rough sketch. Our rough sketch says plot the points and draw a rough sketch of our circle. That's beautiful. Let's do the second part. What is the equation of the circle? Pause the video and try it yourself. Okay, well, the equation of any circle, oops, wrong color, I want to go with white. The equation of any circle is x squared, any circle with the center, x squared plus y squared equals r squared. Let's plug in any one of these points. Let's plug in point P. Minus 5 all squared added to 5 squared gives us r squared. So minus 5 squared is 25. Added to 25 is 50, so r squared is 50. Therefore, our equation of our circle is x squared plus y squared equals 50. Third part of this question says, calculate the length of P to Q. Pause this video and try it yourself. All right, good. Well, if P to Q is based on the radius, we know that this radius is the square root of root 50, the square root of 50, sorry, and the same would be true on this side, also root 50. So therefore, the distance from P to Q is 2 times root 50. Last part of this says, explain why PQ is the diameter of the circle. Pause this video and think how you would explain this. Okay, so one of the ways you could have done this is to speak about the distance. If you could show that the distance from P to Q equals the distance from O to P and the distance from O to Q, it must mean that it lies on the diameter. That would be option 1. The second option would be looking at the symmetry that we've created. There's a symmetry between these 2 points. And because these 2 points are the mirror image of each other, in the case that we've got here that minus 5 and 5 mirrors onto 5 and minus 5, we've got a symmetry. So that's another way we could have spoken about these 2 points. A third option might be to show that they pass through a specific point. You could connect a line and you could work through them like that. So there's a couple of ways, and this is why you would have to have a choice in an exam. As long as you can show this mathematically using correct techniques, you would have got all the marks. The next piece of information we're going to look at is how do we find the equation of a circle that is not at the center. So on the left here, I've got a circle that's centered at C, which isn't at the origin, and another point on the circumference called P. Well, let's think about what we did. We could, again, apply the rules that we know. If I could imagine a right-angled triangle within this, then we would be able to say that the distance from C to P would be the same in terms of Pythag as it was if it was at the origin. Well, let's speak about these. We could say that the x minus a all squared added to y minus b all squared must equal r squared. I'll put these on with color. So this piece here, the yellow, would be the distance that you've traveled from here to here, so x minus a. This one here in blue would be the distance you've traveled from here to here. And then the last one, which we've seen already, this r, is this r here. And so this looks like the distance formula. X minus x1 all squared added to y minus y1 all squared equals d squared, the distance. But this is also the equation of the circle at the origin. And this is the equation that's given on the formula sheet. What we notice here, importantly, again, as you want to remind you about, is that the two, whoops, daisy, that's a highlighter, not a pen. Two important things. This equation tells us two things. The one thing it tells us is the center, and the center of our equation is described by the points A and B. It also gives us the radius. And in this case, the radius would be the square root of r squared. So when we're looking at this, it's important to look here, here, and here. These two tell us where we are, where is the center, and this one tells us how big we are, the radius. You must work in this form for it to be a proper circle and for us to be able to confirm we know the center and the radius. Okay, so let's have a look at an example. F is the point 6 and minus 4, is a point on the circle, and it has a center of 3 and minus 4. Draw a rough sketch, determine the equation of the circle, and then does this point lie on the circle, and does the circle cut the y-axis? I'm going to do all three of these. So first things first. Let's draw a rough sketch of the circle and label the points F. Pause the video and do this yourself. Okay, so on the right-hand side here, we've got a rough sketch of our circle. It's at the point C is the center, 3 and minus 4, and F is the point 6 and minus 4. So that they're both at the same height. Second part says, determine the equation of the circle. Well, we know the following. For any circle, the equation of the circle is described by this. X minus a, y minus b equals r squared. Let's put down what we also know. We know that the center of our circle is at the point 3 and minus 4. And we have another point called F, which is at the point 6 and minus 4. So if we were going to determine the equation of the circle, we would have to use both of these. How would we use these? Well, first things first, let's plug in our center. So if this is A and this is B, we know that x minus 3 all squared and y minus 4 is y plus 4 must equal r squared. So we have our center. We now need to work out our radius, and we can plug in 6 and minus 4. So again, 6 minus 3 all squared added to minus 4 plus 4 all squared equals r squared. And so what do we find? 6 minus 3 is 3. 3 squared is 9. 9 added to 0 gives us r squared. So the equation of our circle in this case is x less 3 all squared added to y plus 4 all squared equals 9. What about part 3? Does the point G, 3 over 2 and minus 2, lie on the circle? Pause this video and try it yourself. Okay, good. So let's test. We're trying to see, does this point sit on the circle? If it sat on the circle, it would satisfy the equation, which means that if we plugged in the numbers, we would get out 9. So we're going to say 3 over 2 minus 3 all squared added to minus 2 plus 4 all squared. We're going to check what that comes to. Well, 3 over 2 minus 3, that's 1.5 minus 3 is minus 1.5 all squared. Added to is 2 squared, so let's do that. And what we find is that it comes to 25 over 4. 25 over 4 is not the same as 9, so therefore it does not sit on the circle. The last part of this one asks, does this circle cut the y-axis? Motivate your answer. Try it yourself, pause the video, and let me know. Okay, good. If it was going to cut the y-axis over here, we cut the y-axis when x equals 0. So let's plug in x equals 0 into our equation. We've got 0 minus 3 all squared added to y plus 4 all squared equals 9. So we've got 9 equals plus 4 all squared equals 9. Let's tidy this up. We get y plus 4 all squared equals 0. Square root both sides, and we solve for y. Does it touch the y-axis? Yes, it does. It would touch the y-axis at minus 4. And that makes sense because all of these points have a y value of minus 4. So the answer is yes, this does cut the y-axis. Let's look at another example. Determine the coordinates of the center of the circle and its radius in this form. Pause the video and try it yourself. Good. Well, there's a couple of things we've got to do here. This is not in the form we want. Remember, the form we want is x minus a all squared added to y minus b all squared equals r squared. What we've got here is an expanded form. And it's at this point that you have to realize we're asking you in a very roundabout way to do something. And the thing we want you to do is complete the square. So something you learned in grade 11. Why do we want you to complete the square? Well, every component of this equation has squares. We need square components. So how do we complete the square? Effectively, you're completing the square on two variables at the same time. So let's do what we need to do. First part of completing the square says we've got to get the x and y coefficients to be 1. So they must equal 1. Well, x squared is originally a 3, and the y squared is originally a 3. So the first thing I'm going to do to all of this is divide by 3. So we've got x squared, we've got 2x, we've got y squared, we've got 4y, and we've got 11 equals 0. I'm now going to do this in pieces. I'm going to deal with the pieces that relate to x with a red bracket. I'm going to deal with the pieces that relate to y in a blue bracket. And I'm going to kind of do the white stuff along the way. So pay attention. Let's tidy this up. Let's rewrite it. X squared plus 2x. I'm going to leave a space. Y squared minus 4y. Leave a space. And I'm going to move the 11 over. And here it is. For the red bits, to complete the square, we would want to add and subtract half of the middle term squared. So half of 2 is 2 over 2 squared. Normally we would add and subtract it, but because I'm going to work left-hand side, right-hand side, I'm going to add and add it on the other side. It would have been negative on the left, it's positive on the right. For the y values, I'm going to add and subtract half of this term, so 4 over 2 all squared. I would normally subtract it on the left, but I'm going to add it on the right. So 4 over 2 all squared. That means the first three terms creates a perfect square here. The next three terms create a perfect square here, and then we'll have a number. Let's look at this. The x comes down, the operator comes down, and this number in the brackets comes down into here. So x plus 1 all squared. The y comes down, the operator comes down, and this number comes into the bracket. 4 over 2 is 2. And the last part we need to do is just add up these numbers. This is 11. Over here, 2 over 2 is 1, 1 squared is 1, 4 over 2 is 2, 2 squared is 4. So I've got 11 plus 1 plus 4, which is 16. We aren't quite done now because we need to tell the examiner what we found. We now know the following, that the center, which is A and B, would have to be the following. It would have to be negative 1, it would have to be positive 2, and the radius would have to be the square root of 16, which is 4. Remember, the reason why this is negative 1 here is because a normally is negative a. So negative times what gives me positive 1? It would be negative times negative 1 gives me positive 1. This stays positive 2 because minus of positive 2 is the minus 2. And this is how you would answer these questions. I'm almost convinced that they will ask you to do a completing the square type of question because it's a lot of algebra involved and really, really good marks. And in the practice today, you're going to see some of these. Okay, worked example number 4. Let's find the center and r when we're given some points. A circle with the center on the line, y equals minus x plus 5, passes through the 2 points. So P and Q are on the circle, and the center of that circle goes across the line y equals minus x plus 5. Determine the equation of the circle. So pause this video and try it yourself. Okay, so there's quite a lot happening here, but let's give ourselves a target. The target we want is to get an equation of a circle, oopsie daisy, y minus b equals r squared. So we need to figure out a, we need to figure out b, and we need to figure out r squared. What have we been told? We've been given the fact that y equals minus x plus 5. Now you need to get into the habit of knowing that if I can convert that equation into a point form, and the point form says is that if I plug in x in this point for this straight line, what will come out is minus x plus 5. That's because x and y are normally points. So I've just rewritten the y with its other name, x plus 5. Now that's quite useful for us because it also means that if I plug in a into this formula, so let's just change the color quickly. If I plugged in a everywhere, I would have, if a goes in, what will come out will be minus a plus 5. And that's quite nice because it gives me an opportunity to solve for a couple of things. I'm going to take the equation we have on the side here and update the original equation we started with. So I'm going to keep, oopsie daisy, I'm going to keep the a as x minus a. But what I do also know is that I could replace b with another name, and the other name I'm going to replace it with is the minus a plus 5. So here it is, minus a plus 5. That's the pair value of it. And that means I've got an equation that I can kind of neaten out a bit. I could say that I've got x minus a all squared, and I've got y plus a minus 5 all squared equals r squared. But now what you know, and you've done a lot of maths, is that they've given us 2 points. If they give you 2 points, the most we can figure out is 2 unknowns. So let's do some clever maths. Let's sub in one of the points. Let's sub in 5 and 8. And we're going to sub it into the equation above. So it's going to be that 5 minus a all squared into 8 plus a minus 5 all squared equals r squared. And we could tidy this up, and I'm going to tie them all up on the next page. But I'm going to first sub in the other points, 9 and 4. So if I sub in the points 9 and 4, that will give me with 9 minus a all squared added to 4 plus a minus 5 all squared equals r squared. Okay, so here are our 2 equations. Let's tidy them up. In the top equation, this first bracket, we can FOIL out, and it will become 25 minus 10a plus a squared. The second bracket, which is really just a plus 3, if I square that out, I'm going to get a squared plus 6a plus 9 equals r squared. And so when we tidy up this, I'm going to be left with 2a squareds. Is that correct? Yes, 2a squareds. Minus 10 plus 6 is minus 4a. And 25 plus 9 is 34. That's equal to r squared. Let's tidy up the second bracket. Second bracket, 9 squared is 81. We're going to have 18a. We're going to have a squared. This bracket here tidies up to a minus 1. So let's just FOIL out a minus 1. A minus 1 squared is a squared minus 2a plus 1. And so what we get then is 2a squared again. We've got minus 18 minus 2, which is minus 20a. And we've got 81 and 1 makes 82. Great. Equals r squared. Now, you've got quite a bit of algebra, but what I'm going to tell you guys to do is look for the following. These are kind of the same scale, and I'm saying that they're both equal to r squareds, which is lovely, and they both have 2a squareds, which is even more beautiful. So let's be smart about this. Let's just subtract. Let's take the first one and subtract the second one. And let's do it like this. We're going to say, put some color in here. I'm going to say the top one minus the bottom one. And let's go. What is 2a squared minus 2a squared? Well, 2a squared minus 2a squared is nothing. What about the next one? Minus 4 minus minus 20 is minus 4 plus 20, which gives us 16. We've got 34 minus 82, and 34 minus 82 is negative 48. And r squared minus r squared is 0. So what we got then is that 16a equals 48. Divide both sides by 16, and we find that a equals 3. If a equals 3, what we already know quite quickly is that if I sub it back into any of the other equations, so let's take a equals 3 and sub it back in up here, I would have 2 times 3 all squared minus 4 times 3 plus 34 gives me r squared. And when we tidy that up, we find that r squared is 40. I also know that from my previous screen, I knew that if x went into minus x plus 5, it would be true that if I plugged in 3 here, it would be minus 3 plus 5, which is 2. So therefore, we've got our center of our circle, and we've got the r squared of our circle. The equation, therefore, for our circle will be x minus 3 all squared added to y minus 2 all squared equals 40. The last thing we're going to look at for this whole section of work for today is how do we tell if circles are touching? Well, let's look here. We've got concentric circles. Concentric circles with different radiuses never touch. It's a circle inside a circle. So in this case, what we can see is that this radius and this radius are different, but they share a center. And so these circles are concentric. They're not touching. What about these circles? Well, let's do the maths again. This radius and this radius, what do we notice about it? Well, if we worked out the total distance between the centers, so this bit, that distance would be equal to the red minus the blue. So radius of the, radius of the big circle minus the radius of the small circle. And when you get the scenario that the distance is equal to the difference between them, what we know is that they touch internally. So they touch internally at one point. And that point's on the edge of the circle. When the difference in radiuses is equal to the distance, they touch once inside. When the differences in the radiuses equal the distance, they touch once inside. What about these circles? We can see that they touch twice, but how do we figure this out using the maths? Well, one thing we know is that the radius of this circle and the radius of this circle and the distances between their centers, what does it tell us? It tells us that the distance, in this case, between the centers is less than what would happen if we added the red radius to the blue radius. And that makes sense because there's a small little bit of overlap. And you can see that overlap happening in the part of the circles. So when the distance of the centers is less than the sum of the two radii, what we get then is circles touching at 2 points. So they circles touch at 2 points. So let's just go back for a sec. When the circles radii add together and it's greater than the distance, the circles touch outside at 2 points. Let's look at this last one. We can see by the drawing that they touch once. Let's figure out this maths. That radius added to that radius is the same as the distances between them. So here we can see that when the distance is equal to the sum of the radii, what we get is touch once external. I'll write this. Touch once external. Again, let's go back to remember what we saw. When the distance of the radius is touch once on the outside, we've got the sum of the radii. And the last one for today, what we can see in the drawing is the following. We can see that this radius, if I added it to this radius, would not be the same as the distance between them. So in this case, the distance is greater than the sum of the radii. If you find a scenario like that, then the circles do not touch. So it's important for you to know these components. Whenever they ask you, do circles touch, we're comparing the distance between the centers and how they compare to the radii of the two circles. I hope you've enjoyed this session. We've got quite a lot to practice in today's work. And yeah, really been good chatting to you guys. Hope you're all well.